we'll get started. So there are a few corrections to the previous lecture. I made a few minor mistakes, so I wanted to note them down. And I'm referring to the YouTube video. So now YouTube video is the reference for us. So at 47:39, the integral is supposed to be from t naught to so the lower bound in the integral is supposed to be t naught. So in one of the integrals, I've written 0. So can you change it to t naught? So this was about, if I'm remembering correctly, as2 integral t naught to t s2 as1 ds1 ds2. It's something along this line. So make sure that this is t naught and not 0. The other correction is at 108:32, and there the definition of AT should be gradient of x ft phi t transpose. So this was missing. And I realized that the book is using a different notation than what is customary in the optimization literature. So in optimization, the gradient expression is something that I'd given in the class. And it turns out that in differential equations, people don't write that transpose, but they still mean the gradient. So anyways, and the same mistake also happened at 1:11:24. BT should be, I should write both AT and BT there. And this is in R n cross n. This is in R n cross m. So again, the transpose was missing. I was giving you the notation from the book, but turns out that the convention is quite different in the book in comparison to the optimization convention. Okay, so the transpose is missing on these 3 places. So please note it down. And you can go back to your notes and you can maybe make that correction right now. Okay, so these are the corrections. Okay, any questions so far? So I'll give you a brief recap of whatever we have done so far. So what we have said is, I have a differential equation, x dot t equals to f of t xt, xt0 equals to x0. So the first statement we talked about was if f is continuous, implies there exists a solution. F is Lipschitz in X, implies there exists a unique solution. Then the third result we talked about. I mean, we talked about many things, but these are the four important things moving forward. The solution xt is of the form of this form, and then this becomes matrix exponential in the context of time invariant system. One property that phi satisfies, and you can go back to your notes and you can convince yourself that that is the case. So if you have the same argument for t, then it should be identity matrix for all t, and then d over dt and the other thing was that phi of t comma t naught equals to exponential a t minus t naught if at is identically equal to a for all t. So this is just a recap of whatever we have done in the previous lectures. And I have a question for you guys. The question is, I was driving my car to work today and I was accelerating and something came in front of me and I started braking pretty hard. And so in some sense, I was in a situation where my action ut was not Lipschitz. Okay, it was not a Lipschitz continuous action. So let's focus on the following problem for the time being. I am at x dot of t equals to f of t xt ut. When I'm driving the car, of course, the function f doesn't quite depend on t. It's not like the mass of the vehicle or any parameters of the vehicle changes quite significantly with respect to time. So this t is not there. And what I have mentioned earlier is that if f is continuous, then there exists a solution to this particular differential equation. So if u is a function of time, ideally we want this entire thing, I can write it as, let's say u, this is my psi of xt or t comma xt, then I can write it as f of t comma xt. So I was looking at the state, I was looking at what's happening on the road, and then I was taking an action. So my control policy, this psi is actually my brain. So this, my brain is looking at what's happening outside, looking at the state of the system, and then mapping it to the control action, which is my steering, braking, and acceleration. Those are the three things that I control when I'm driving my vehicle. So it turns out that psi was actually not Lipschitz continuous. Consequently, this composite function is no longer Lipschitz continuous in x. So this f is not Lipschitz continuous in x. But I still arrived here, right? I'm standing in front of you. So this one is saying, if f is continuous, then there is a solution. And it turns out that while I was driving to work, f turned out to be not continuous. And there is still a solution. And the solution is, I'm able to reach the university on time to teach this class. How do we fix this problem? The problem is, theory says f has to be continuous for me to get a solution, and f has to be Lipschitz to get a unique solution. And we saw some examples in the class where you had a non-unique solution, there was no solution, you had a non-unique solution, or you had multiple solutions, right? So non-unique is multiple solutions. And I'm saying that, look, I was driving and this is no longer continuous, so it doesn't meet the first requirement. How do we fix this problem? Any thoughts? What would you do? Yeah.
If learning is specified interval until the final continuous part, and after the
Yeah.
continuous part, it becomes complete again. That's like two different.
Wonderful. Okay, that's great. So what he is saying is that actually there were two functions. There was one function before I did the hard brake, and there was another function that happened after I did the hard brake. And so I have two separate functions, and each of those functions are Lipschitz continuous. Therefore, we have a solution. Okay. So at the time of discontinuity, what happens, right? So the limit of the state before becomes the new state for the new differential equation that happens after the discontinuity start. So that's going to be my next result, which is we can extend this idea, number one idea, to f is piecewise continuous. Okay, so if everybody understands what piecewise continuity is, so f is continuous for some time, you have a discontinuity, then f is continuous for some time, then you have a discontinuity, then f is continuous for some time. So that's piecewise continuous. And so if f is piecewise continuous, we still have a solution because because of the following reason. So let me write it down formally. F t comma x is continuous. I'm going to write CTS for continuous moving forward because we are going to use continuous many times. So I'm going to write CTS. So ftx is continuous in the interval t naught less than equal to t less than equal to t1. And so on. Okay, so I have discontinuities. So in this particular definition, what I'm doing is I'm dividing the time and I'm talking about piecewise continuity with respect to time. You could also have piecewise continuity with respect to state. Generally, those kind of problems are studied under the umbrella of switch system. We are not talking about switch system here, so we don't care about it. One example of a switch system is when you are driving your vehicle and the gear changes. So then your dynamics change, your state dynamics change, and that's a switch system. So, but we are talking about continuity, piecewise continuity with respect to time. So, for every, remember this is closed T naught, but open T1, closed T1, open T2. So you can have discontinuities at T1, T2, and so on, and that's fine as long as you have continuity in the middle. You still have a solution. And the way to get to the solution is as follows. F is piecewise continuous, then I'll have a solution phi t is a solution defined as follows. So phi t equals to and now here is where things change. Okay, so this is the important part that I wanted to emphasize. So I'll let you guys write it down and then you do the same thing. Okay, so whenever we have piecewise continuity, we can solve the problem by uh, just changing the initial condition for each piece of the puzzle, right? So this is a very big puzzle. Initially, we do things the way we have been taught so far, but at time t1, where the function changes value, where the function is not Lipschitz, it might have a sudden discontinuity or sudden jump. In that particular case, we look at the limiting state of at time right before t1. Okay, so t1 minus 0.00000001. You look at that particular time interval, look at what the state is, that becomes your initial state for the next round of solving the differential equation, in which case you will get a solution, and in case all of these are Lipschitz, you get a unique solution, right? So the way to do it is by piecing together the puzzle and get the trajectory of the system over time. Yes.
Because iteration only defined in the first interval.
Which one? This one?
Yes.
Yeah, it's only defined in this particular interval, right? Because it's a piecewise continuous. So I know that this is continuous in this particular interval. And then there is a solution to this differential equation. Then by changing the initial condition for the second differential equation, I'm able to piece together the entire trajectory, entire solution of the differential equation. Any questions so far? This kind of argument will not work if you have infinite number of switching in finite time interval. Those are, of course, mathematical stuff. It doesn't appear in real world. So what would appear in real world is you will have a lot of cycling, which is that the system turns on, then turns off, then turns on, then turns off. So one of the things you would notice in your own house is, because it's so cold outside, your furnace might be cycling at this point of time. So the furnace turns on, then the temperature gets reached, then it turns off, then it stays off for maybe a few minutes, and then the temperature drops again, and then it turns on, and then it stays on for some time, and then it turns off. So that's called a cyclic behavior. And that kind of behavior, of course, you have like a piecewise continuous kind of behavior in that case, because again ut is going to um, become 0, and then it will become 1, and then it will become 0, and then it will become 1, and that's completely fine because it's piecewise continuous and you have finite number of discontinuities in a finite time interval. But arguably speaking, you can come up with examples of ut in math. It doesn't happen in real life, but in math you can come up with examples of ut where you have infinite number of switching in finite time interval, in which cases this particular approach is not going to work. I think in those cases there is no solution to the differential equation also, but I may be wrong. It's not something that we teach or we study in engineering classes. Any questions so far? Okay. The next topic I want to talk about is a non-homogeneous equation with a forcing function. So let's try to solve that problem. Can I erase this board? Okay. Okay, so let me introduce the. I need the stuff on the board, so I'll just keep it. So I have the problem x dot t equals to at xt plus gt. For the time being, assume that a is a continuous function of t, g is a continuous function of t. You can of course replace it with piecewise continuity, but for the sake of ease, I'm going to just keep it simple and assume that these are all continuous functions of time. So this one has a solution like this. The question is, what is this? What is this? This function is known as forcing function. I mean, it is called forcing function in the book. It doesn't, you don't necessarily have to call it a forcing function. It could be just a control input, or it could be heat provided to the system or whatever, right? It doesn't matter what you call this function. In the book, it's called the forcing function. How do we solve this problem? Well, one way to solve this problem is to go through the Picard iteration that we introduced in the previous class and do all that math, do all the integral, and try to solve this problem. But we also know that this is a Lifshitz continuous function with respect to x, because a t is bounded. So it has a unique solution. So if I can come up with a solution just out of my hat, because I'm extremely experienced in differential equations, I can sleep at night and I wake up in the morning and I cook up a function that I think is a solution to this problem. And then we can try and verify that it is indeed a solution to the problem. So let's do that. Let's try to cook up this particular function. I'm going to keep it a function of, this is the solution to this differential equation. It's a function of the current time, the initial time, and the initial condition. And I'm going to define it as phi of t naught x naught plus This is this capital phi, this is small phi. These are all capital phis. This is an Rn. This is a matrix. Okay. The constructive way to come up with this solution is Picard iteration. We are not doing the constructive thing right now, but we are not doing destructive thing either. We are just doing things. Okay. So what are we going to do? I'm going to differentiate this function with respect to t, and hopefully, because I pulled this solution out of my hat, I don't have a basis to assume that this one is indeed the solution or not. But if I differentiate this with respect to t, it must satisfy this differential equation, right? So let's do the differentiation with respect to t here. So I'm going to differentiate both sides with respect to t. So I have d over dt I have d over dt okay. So now we are in an interesting situation. So I have t twice here, I have one t here, and I have one t here, and I'm taking the derivative with respect to t. What should I do? So I have two t here. One is inside the integral, one is as a limit of the integral. Anyone knows how the differentiation of this kind of stuff is? No? So it's actually easy. So I'm writing s equals to t because technically what happens is when you take the derivative only with respect to the integral, so what happens is wherever you see s, it gets replaced with t. So that's why I'm writing s equals to t, because I'm going to replace this with t. And then the second one is going to be the integral So whenever you have an integral and you have a function of t and you're taking the derivative, first you take the derivative with respect to just the limit, and then you take the derivative of the function inside the integral, keeping the limit as the same. So the limit hasn't changed. It's still t naught to t. I've just pushed the differentiation inside. I know it may not have been taught to you before in the calc class, but the proof is very simple and straightforward, and generally taught in some advanced calculus classes. What is this term? What is derivative of the capital phi? The derivative of the capital phi is AT times phi itself. We did the proof of that in the previous lecture, so it should be there in your notes. So this one becomes AT x naught plus what is phi t comma t? That's identity. So I have gt. What about this term? This is integral T naught to T, AT, PT T naught, sorry. AT doesn't depend on S, right? This one is not dependent on S. I'm just taking the derivative of phi with respect to T. So I get this expression, it's not dependent on S. So actually I can pull this outside of this integral. So does that give us something? This looks like a lot of equations, but does it simplify? Does it simplify? I have this term 80 times this, and I have 80 times this integral. So I have 80 times phi t naught x naught plus integral so I get something. What did I get? Oh, I get this phi. So this thing in the parenthesis is actually my solution itself. So this is equal to 80 times phi t naught x naught plus gt. So the derivative of phi is 80 times phi plus gt, which is x dot t equals to 80 xt plus gt. So it's essentially having the same derivative. All I have to see is at time t equals to t naught, what is the value of this function. Anybody wants to tell me what phi of t naught x naught is? So it does satisfy this thing I pulled out of my hat does satisfy this differential equation, but it may not satisfy the initial condition. So I still need to check what happens to the initial condition. So let's do that here. So my phi of t naught x naught is capital phi of t naught x naught plus integral t naught to t naught what is integral of something where the lower limit is the same and the upper limit is also the same? That's 0. So this one is 0, this one is identity. So at t naught, phi is exactly equal to x naught. Okay, so I'll let that sink in, and I'll pause here for questions. Okay. So what did we do? We had this differential equation with a forcing function. I know how to solve this problem. I don't know how to solve this problem. So how did I solve this problem? I solved this problem through Picard iteration, and I did a lot of calculation, and then I defined this matrix which has the time derivative satisfying certain criteria and so on. And in case AT was identically equal to A, it led us to matrix exponential. And then I said, look, we need to solve this problem. And I propose that, look, this looks like a potential solution to this problem. We know that there is a unique solution to this because this is all Lifshitz and it has all the nice properties of continuity and Lifshitz continuous and all that stuff. So it must have a unique solution. And so I came up with a potential candidate for the solution. And then what I did was I took the derivative, time derivative, turns out that it satisfies this differential equation. I set time t equals to t naught. It satisfies the initial condition. This differential equation is supposed to have a unique solution, so this must be the solution to this differential equation. Okay. I want you guys to notice something very interesting in the solution to this differential equation. So anything interesting here? Let me erase all the things that are not useful, because I want you to notice something interesting in this solution. So let's see, this term seems to be the same as this term, right? So I didn't have a forcing function here, my gt was identically 0, and it seems to me that this solution has one element as this particular value, which comes from this expression. This one, on the other hand, is the solution if x naught was equal to 0. So let me write it formally. So I have x dot t equals to at xt plus gt, xt naught equals to 0. So my initial condition is 0. So I only have a forcing function, but I don't have any initial, or rather my initial condition is equal to 0. In this case, my solution I'm going to call it a particular solution. I'm going to call it phi p of t, t naught, x naught is just integral and I'm going to call this x dot t equals to at xt plus 0. So my gt is equal to 0 and my xt naught equals to x naught, and what I get is called homogeneous solution. And my function phi equals to the sum of particular solution and homogeneous solution. I'm going to call it particular solution homogeneous solution. So what is the homogeneous solution telling us? So it's basically saying that I have an initial condition, I don't have the forcing function, so the system is actually behaving naturally. It's the natural behavior of the system given an initial condition. So my initial condition is given, I don't have a forcing function, this is the natural solution that I'm going to get of the trajectory of the system due to the initial condition, and that's called as homogeneous solution, and that's denoted by phi h. On the other hand, if I did not have an initial condition and I'm going to add this forcing function to the differential equation, then I'm going to get a particular solution. This is particular to this particular forcing function. Okay. It turns out that the solution to this differential equation, which has a forcing function and which has an initial state, is actually the sum of the particular solution and the homogeneous solution. The reason why we have this is because it's a linear system. Okay, as soon as we remove the linearity, if this was a non-linear system, we won't have that property. Okay, so that's the benefit of having a linear system. And as I had mentioned in my previous class, if you look at the nominal trajectory and you look at the perturbations to the nominal trajectory, you can come up with a linear dynamical system for the nominal trajectory. And along the nominal trajectory, assuming that the function doesn't really change much within the vicinity of the nominal trajectory, you will have this sort of behavior where you will have a particular solution and an homogeneous solution, and the sum of the two will give you the solution to the trajectory, the new trajectory of the system. Remember that this is a vector in Rn. So at every point of time t, you get a vector in Rn. That's the state of the system. When you're driving the vehicle, what are the states? Your velocity, position, heading angle, those are the typical states of the system. So you'll have like 5, 6, 10, 15 dimensional state. Actually, let's think about it. So when you're driving the vehicle, certainly your xy position, the velocity of the vehicle, and the heading angle of the vehicle. So those are the three natural states of the system. What else could be a state of the system? And I'll give you an example. The distance to the next stop sign, that's the state of the system. And the reason why it's a state is because I need to stop at the stop sign. That's a law. As a result of which I need to put that in the state of the system. So that increases my state. What else is a state of the system?
Distance to other cars.
Yeah, distance to the other cars, especially the car right in front of you. And if in case you want to switch to the different lane, then you have to know what the cars in the other lanes are doing. So that also becomes the state of the system. Yeah. What condition the other car is in? What? Okay, yeah, definitely. You need to predict what the other car is going to do on the road. So that definitely prediction of what the other cars are going to do on the road is.
The composition of the asphalt before the road.
Okay. I didn't quite get that. Can you say that again?
Like the physical condition of the road.
Oh, physical condition of the, well, yeah, I guess in this weather, I guess that's also a state variable. So you look at the physical condition of the road. In fact, I will tell you that I skidded in the garage a couple of days back when I was taking out my car because it was all black ice on the floor. So certainly you could have situations like this where you have to look at the state of the system, and the state of the road actually becomes part of the state of the system. Technically speaking, it's a parameter, but if it is changing every now and then it becomes a state. It's not just a parameter. A parameter is something that remains constant for quite some time, like for instance, mass of the vehicle, which kind of remains constant for a trip. But if it is changing every minute or every second, then it's almost like a state of the system. Okay, so state of the road, definitely. What else? You know, pedestrians, the state of the pedestrians. If you're driving around on campus, a lot of people are on their phone while they are crossing the road. I hope you guys are not one of them. I see a lot of nodding heads, but yeah, it's not a good thing to do. So pedestrians and distracted pedestrians, those are also state of the system, because your control action actually depends on what the state is doing. Perfect. The traffic light signal, whether it's red, green, yellow, that's also part of the state of the system. Distance to the traffic light is the state of the system. So those are broadly the state of the system. If you're driving on a highway, Then the distance to deer or distance to wild animals is also a state of the system. I was driving a few days back, and a dump truck, something fell out of the dump truck right in front of my vehicle. Turns out I didn't consider that as a state of the system until it became the state of the system, and I had to swerve my car in order to save myself. So some such things can also happen. Wild things can happen when you are in the wild, and so your state of the system would change accordingly. One of the biggest challenges with autonomous driving companies, by the way, autonomous driving algorithm, is the fact that you don't quite know some of these states of the system, um, because you don't think of them as a state until you actually encounter that situation, and then you add it to the state of the system, and now your state becomes larger and larger. So that's what the autonomous car companies are doing for a long time. One of the things that my friends told me with one of the cars that he has, because I'm on camera, I can't take the name of the brand. But the problem with that particular vehicle and the autonomy stack in the vehicle was that that vehicle assumed, the state description of the vehicle assumed that everyone else is going to drive according to the law. And in his opinion, that was the wrong assumption. From the driver's perspective, because when you are driving on the road, you kind of know who is not going to follow the law, right? So if you're at a four-way stop sign, then there is a preference order as to who is going to cross the intersection first, but some people may not want to stick to that preference ordering. So that particular brand's car assumes that it's my turn to cross the road, and so I'm going to cross the road, but the other person has better idea and maybe in a hurry or whatever, and so they cross the road, and then the car takes a misstep. So anyways, those are some things that you really worry about when you are talking about designing control algorithms for systems of this type. I mean, in general. So something that we don't worry about in this class, but as soon as you take up your first job, you will have to worry about it. Okay. So we finished the discussion from chapter 1 with this, and now I'm moving on to chapter 2. I want to talk about this input output equation, and I want to spend some time on this because it's an important topic. I have x dot t equals to f t x t u t, and I have yt equals to, I hope it's g. Yeah. So this is the state equation. This is the observation equation or measurement. I have to give the initial condition. So my x of t naught equals to okay. So there is a state equation, which is a differential equation. There is an observation equation, which is not a differential equation. It's just actually measuring what the state of the system looks like, but sometimes the control can also influence the observation. So think of it as you are heating a kettle or something, So the state of the system would be what the temperature of the water is in the kettle. UT is how much heat is, or what the temperature of the surface is. That could be UT. So if you put a thermometer in, you might not just measure the temperature of the water, but you could have some noise or some linear combination of UT, which is the temperature of the bottom, could also get added. And so that's the temperature you would be measuring. Okay, so sometimes the observation equation includes some element of the control variable, and that's why we write it as YT. Now, the other name for this is measurement equation. So I tend to use observation equation in my paper, but I have seen people using measurement equation in some cases. And the idea is this is the state of the system, but this is what we can actually measure based on whatever sensors I may have. So I'll give you a very complicated example that one of my undergraduate thesis student is working on. So he's trying to understand epilepsy seizures in collaboration with another Buckeye graduate who is now a faculty elsewhere. So we are trying to look at seizure. Now, what happens in an epileptic seizure? Something in the brain, there is some circuitry within the brain. I don't quite understand it, so pardon my ignorance. But something inside the brain goes unstable, as a result of which you have the patient has seizure. Now, the state equation actually is what's happening inside the entire brain. But can we measure it? Can we measure what's happening inside the entire brain? Well, there's no way to measure it. All we can do is put electrodes on top of the skull, and we can measure some variables. So in the data sets that we looked at, this YT is 50 dimensional, 100 dimensional, 78 dimensional, 85 dimensional, depending on which doctor and which hospital measured that particular patient. Now that YT is giving us some information about the state, but it's not really measuring the entire state. If you think about aircrafts have pitot tubes, which measures the airspeed. Now, of course, on an aircraft is very big. So the air is flowing all over the aircraft, including the wings, including the body, fuselage, tail, and so on. But the pitot tubes would be in like 5 or 6 places on the aircraft, or maybe 10 places on the aircraft. So that's measuring the airspeed at those 10 or 5 or 15 points, but not the entire the speed of the air across the entire fuselage or the body of the aircraft. So the true state is very complicated, but what you can measure is what you know about that particular system. And if you cannot measure it, you don't know certain things about that particular system. So in the case of epileptic seizure example, you don't know what the state equation is. You make some observation, and then the doctors try to figure out what sort of surgery is needed in order to control the state. Okay, and then they do something like some surgery, and then the patient becomes fine or may not become fine, whatever. That's the story for the later. But basically, based on the observation, if you don't have the complete observation, you may not be able to control the system perfectly. If you have a good observation of the system, then you will be able to design the controller, which is UT, in a desirable way so that XT is in a desirable zone. Now, this equation is known as input-output equation of the system. So you have UT, which is the input, you have the system, and you have the output YT. Okay. So YT is a function of all the inputs that the system has seen so far. One thing that I'll tell you is, as knowledge evolves, as science evolves, you get better and better understanding of the state equation. So let's go back to 1600s. We saw planets moving, we saw stars moving, we saw lots of stuff moving in the space, but there was no knowledge of the theory of gravitation. We didn't have the state equation that governs the celestial bodies. And so people thought, Earth is the center of the universe, things revolve around Earth, and then somebody obviously pointed out, oh look, the Jupiter was seen here, but now it's there, so Earth cannot be the center, so something else is at the center. Then somebody said, okay, well, the sun is at the center of the universe and everything revolves around sun. And then somebody else pointed out the anomaly that, look, the North Star is there in summer, it's somewhere else in the winter, whatever. So that's also not true. And then they've realized that, okay, there is a galaxy which is called Milky Way, and maybe the center of the Milky Way is the center of the universe and everything revolves around the center of Milky Way galaxy, but that also turns out to be false. And now I don't know what the current state of affairs is, okay? But what I do know is that the theory of gravitation has been tested over 400 years and it appears to be correct. And so somebody, which is Sir Isaac Newton, he spent a lot of time figuring out the state equation of the universe, of the celestial bodies. Okay? Now we know what the state equation for the celestial bodies look like. But for human brain, we don't quite understand it yet. Okay? So as time progresses, we will know more and more state equations. But at this point of time, for something like a human brain or something like a human body, you know what the input is, you know what the output is, you don't know what's happening inside the system. Okay, so you don't have the internal description of the system. And of course, people at Ohio State and elsewhere are working on figuring out some of those internal states of the system. But for something like a air conditioning system, your furnace, your vehicles, your suspension in the vehicles, we understand the state equation very well. Okay. Now let's assume, so I've written it as ut as input and yt, maybe I should write it as u as input and y as output. So u is, I'm going to use continuous function, but piecewise continuity is also fine. So u is r2, maybe r cross rn to rm, and y is c r cross rn cross rm, no, rt. So this u takes as input state as well. So u is a function of time and state. So the book talks about both cases where u is a function of only time and u is a function of time and state. Generally speaking, most of the systems have closed loop control. And in order to close the loop, you of course need better sensors. So people are designing sensors and they are closing the loop. So u is generally a function of time and state. But I want to admit here that you could have situations where u is just a function of time, not a function of state. In order to make something a function of state, you need to have the measurement device for that particular system. I'll give you another example of that. I don't know how many of you attended a seminar a couple of days back, maybe last week, where the seminar speaker was talking about a new sensor he has developed for measuring the iron content in a molten ore. Okay, so it's a very complicated sensor, but for some reason right now, if you have a molten iron ore and you want to test what is the iron content in that molten liquid, you have to take out that liquid and then you have to take it to a lab and then you have to test it, and then you will know, okay, this is 75% iron, 55%, well, no, 75%, and then 25% something else, nickel, copper, whatever, cadmium, and so on. But now he has built this sensor. You put the sensor in the molten liquid, it gives you what the iron content is right at that point of time using the spectral analysis of that particular liquid. Isn't that cool? So something that was not measurable 5 months back became measurable today. Okay, so that's the role of sensors in these systems. So until now, this whole iron refining process was open loop. Now there is a hope that the iron refining process will become, in real time, it will become closed loop. So who knows? Okay, Maybe some of you will actually develop that control system, okay, after taking this class. But anyway, so this u is a function of time and state. In some cases, u may only be a function of time, not of state. But let's assume that in this case, u is a function of time and state. Okay. So we know that the solutions for these class of systems would exist if things are piecewise continuous. But one thing that we are interested in is if y is a linear function of u. But remember, until now, like prior to linear systems theory class, by linearity you meant or you thought about matrix multiplication. Now, because these are general spaces, these are linear vector spaces, we have to think of system as a linear operator. No longer, we don't use the matrix anymore, we are going to use the linear operator now. So let's assume that my x dot t equals to at xt plus vt ut and yt equals to ct xt plus dt ut. So both f and g are linear functions. Then in this case, the solution and xt naught, x naught. So this is my gt function. So remember we talked about gt a few minutes back. This would be my gt. This is at xt plus gt. So I know what the solution is going to look like. This is so let's dissect this a little bit. So I'm going to expand on this phi term. So I get yt equals to ct phi t t naught x0 plus ct integral t naught to t and I want to remind you this is our n cross n, this is our n cross m, this is our m. Okay. Anything interesting you notice about yt as a function of x naught and as a function of u? What's the interesting thing you notice? So what I notice is my yt is a matrix multiplied by x naught plus some integral which is linear in u plus a term which is linear in u. Okay, so my yt is a linear function of x naught and u. But this is actually a linear operator acting on x naught and well, in the case of yt, the linear operator on x naught is actually a matrix. So this one is a R P cross N matrix, right? And this one is actually a kernel function. Well, yt is a linear operator over the space U. So I'm not sure if you guys see why this should be a linear function of U, but I just want to show you why this would be a linear function of U. Any questions so far before I jump onto that? Okay, everybody understands where I got this solution from. We just talked about it 10 minutes ago or maybe 30 minutes ago. We derived this expression. So this is my GT or GS. And so I get the expression from there. I substitute it in the expression for yt. So yt is ct times xt plus dt times ut. So this dt times ut comes here, and I replace my xt with the solution that I've computed, so which is given here. And then I notice that yt is a matrix multiplied by x naught. So it's linear in x naught and it's linear in u. Now I want to show you why it's linear in u. So let me write y as the operator over u, and let's assume that x naught is 0 for the time being. Okay, so this term gets cancelled. This term doesn't appear. This term is 0. So then I get yt is equal to ct integral t naught to t so t is linear. Can someone tell me what the definition of linear operator was from your notes, if anyone is taking notes? We had done that linear operator thing too. Yeah.
Like if we transform two different vectors of matrices, we can like dissect them into linear components for each
So t of
we can put constants at the outside.
right. So u1 plus t of u2 and t of alpha u equals to alpha tu. Right? That was the requirement for t being a linear operator. Does y satisfy these two criteria? So what happens if I replace this u of s with u1 plus u2 of s and this u of t to u1 plus u2 of t? So is this t a linear operator? So I have y of, so pick u1, u2 in C R M. So for the time being, I'm looking at open loop control. So it's this is the time axis. This is the M action that I'm taking. So I have a linear operator. So what do I get? Let's say y1 and y2. So when I have u1 as my control sequence or control signal, then y1 is the output, u2 is the control signal, y2 is the output. So U1, so think about it this way, U1 is I'm going to drink 2 glasses of water every day, and Y1 is how happy I am throughout the day, and U2 is I'm going to drink 1 glass of water every day, and Y2 is how happy I am at the end of the day. Now I'm going to try and figure out what happens if I drink 3 glasses of water every day, okay? And assume that my body is a linear system. Okay, so what happens? Let's see if the math tells us whether I'm extremely happy or not. I don't trust my body, but I trust math. Okay, so I have T of U1 plus U2. This is Ct times integral. I'm getting tired. I wish the department gave me an easier course to teach. So I get this. Is integral a linear function of the integrand? Right? So the integral of sum is sum of integrals, right? Something that we all know of. This is also, you can distribute it. So what I get is, this is y1 plus y2. So you were right, I will actually be very happy after drinking 3 glasses of water. So this is what I'm going to do today. And you can see that the same thing will happen if you multiply u by alpha. So if you scale u, the y will also get scaled appropriately. So this condition will also hold true. So in this case, this is actually a linear operation over the actions that you are taking. Okay, so for this linearity, what I had assumed was x naught is equal to 0. So I don't have any initial state. My initial state was equal to 0. I looked at the output as a function of input. Turns out that that particular input-output expression is actually a linear expression in the sense that the output is a linear operator over the input. What happens if I bring x naught back into this particular equation? So now I have some initial state x naught, and I'm looking at y1 and y2 with that particular initial state. So I need to erase something. So let me erase this thing. Any questions so far on this? No? Okay, so now let's say my y1 equals to t of u1, but my x naught is not equal to 0. y2 is t of u2, and my x naught is not equal to 0. It's the same x naught. So the x naught remains the same in these two systems. I'm interested in t of u1 plus u2. Is it equal to t of u1 plus t of u2? So I started my day very happy. So x naught was not equal to 0. Then I had 1 glasses of water and 2 glasses of water. Now what happens? Do I have this linearity or not? I actually don't. And the reason is this term is going to get added twice. So my t of u1 contains this term because my x naught was non-zero, My T of U2 also contains this term because my X naught was non-zero. Now I add the two terms, I get 2 times this particular expression. Okay, so it's T of U1 plus U2 is not equal to T of U1 plus T of U2. Okay, so just because you have an initial condition implies that you're no longer have that linearity if you don't assume that the initial condition is also changing. So that's the problem. Nonetheless, it is linear. Yt is linear in x naught. Yt is linear in u. But if you add the two things together, it's no longer linear. And we have the same expression here. There is a homogeneous solution which is due to the initial state, and we have a particular solution which is due to the actions that we are taking. So when we look at the input-output equation, so we have the input, we have the output y. I'm looking at, these are the only two things I can see, what I'm feeding in and what I'm getting out, if I don't know the internal model of the system. So people like Newton and Einstein and Niels Bohr and various people, they have identified the physics, chemistry, biology of systems, and they understand the internal description of the system. So then we have a state space. But if we, in the absence of the understanding of the state expression, state equation, so in the absence of this particular equation, all I can see is what I'm inputting and what I'm getting out. And what I'm getting out is purely a function of the sensors that I have or the measurement devices that I have. If I don't have a measurement device, I'm not observing anything about that particular system. So when you look at the input-output behavior of the system, y as a function of u, we try to understand t, or we try to understand the properties of the function t, the map t. So we talked about linearity just now, but we also talk about, we consider or we think about memoryless property of t, we think about superposition property of t, we think about causality, and then we think about time invariance properties. So those are the different properties that we'll talk about in the next class. One comment or rather definition that I want to make, if y t is in R1 and ut is in R1, then this is called single input, single output system. In short, SISO system. And this is what you might have studied in signals and systems and feedback control systems in your undergraduate. On the other hand, if YT is in RP and UT is in RM, then this is multiple input, multiple output system, which is MIMO. So CISO systems are easy systems, single input, single output systems, easy systems to understand. Generally speaking, people tend to use Fourier transform and Laplace transform and all the machinery, Bode plot, Nyquist plot and whatnot to design controllers that are for CISO systems, which has been driving a lot of the stuff in the world today. But now we have more sensors, we have more actuators, so we have like multiple input, multiple output systems, and then the control design process becomes slightly more complicated, and we'll talk about that in the rest of the semester. So that's all I have for today. We'll talk about different properties of this operator T, and we'll study different examples of this operator T, and then we'll figure out what else we need to take. But right now I'm covering chapter 2. You can ignore everything that is on discrete time systems in chapter 2 and just consider the continuous time system stuff in chapter 2. So we'll talk about it in the next class, and we'll talk about impulse function and impulse response of the system in the next class. So thank you.